Hello everyone. So today we are going to be talking about a problem from CCC 2024. And this is the fourth problem in senior, which I think is a bit easier than an S4 normally is. But it's basically like a graph problem. It's not too hard, not too easy, but normally S4 is a bit harder. But anyways, I'm just going to assume like that you have a basic understanding of graph theory, of what a graph is, how to implement a graph, how to implement some graph algorithms, and maybe some terminology. So let's get into it. So first of all, let's read the problem statement. So let me make this slightly bigger. So Alana, the mayor of Kitchener, has successfully improved the city's road plan. Okay, so that's a reference to CCC 2023, I think, a problem last year. So, however, a traveling salesman from the city of Red Blue complained that the roads are not colorful enough. Alana's second job is to paint some of the roads. So this city has n intersections with m roads. So by intersections, they basically mean nodes in a graph. And by roads, they basically mean edges in a graph. Where the ith road connects intersections ui and vi, so these are all given in the input, all roads are initially gray. Alana would like to paint some of the roads in red or blue such that whenever there is a gray road that connects two intersections, so any two intersections, there is also a path of roads from like one intersection to the other, such that the roads on the path alternate between red and blue, without any of the roads on this path being gray. To lower the city's annual spending, so they want to minimize the number of painted roads. Okay, so let's think about how we would do this. So whenever there is a gray road that connects two nodes, we have to essentially have another path that alternates patterns. And we want to minimize the number of painted roads. So something that immediately comes to mind, when you hear you have to connect like all the nodes with the minimal amount of edges that maybe satisfy a certain condition. Well, the first thing that really came to my mind is to create like a spanning tree. So in a graph, if you have a spanning tree, so a spanning tree is basically a tree that is like a subset of this graph's edges, which still connects every node. So for example, like if we have, how can I draw? Okay, so if we have a graph like this, then something like I don't know, this would be a valid spanning tree. So it doesn't use all of the edges, but it still connects all of the nodes. And if you see like this like red part is a tree, which means that there's only like one simple path from any node to any other node. So if we want to minimize like the number of unnecessary roads, then basically what we want to do is create something like a spanning tree. Now, the first thing that came to my mind was to create like a minimum spanning tree with an algorithm like Kruskal's algorithm, but this ended up not working, possibly because my implementation was wrong. But basically, a very simple idea is to start from any node, so like randomly take a node. So let's say like we start from this one. And then what we want to do is basically create a depth first search outwards. So we sort of branch out into the graph and we perform a depth first search. And at each level, or at each depth, or like for each edge that we go further from the beginning, then we color it an alternate color. So what that does is we start from a node, and then sort of like the paths that are leading out of this node are all like alternating colors. So that's something called a DFS tree, which is a tree that's formed by depth first search. Now, DFS, I believe it is guaranteed to like generate a tree when you start the algorithm from any node, and then proceed to like mark every node as visited. But I'll just like give a demonstration to see what I'm rambling about. So let's say we start with 2, right? So we go outwards and we perform a depth first search. So we basically branch out from here. We branch out here, and let's just say we start by coloring this edge red. Okay. And then it's a depth first search, which means like we go like on like this direction, in this direction. We don't start branching out into these first because that is a breadth first search, or BFS. But here we're doing a depth first search, or DFS. So we're going to like branch out fully first until we can't anymore, which is gonna look something like this. So now the order that we actually go from here is, well, it doesn't really matter in theory, but that just depends on how we implement it. So let's say we like go from here, and then, okay, so here's a blue edge, and then we keep going from here to like all of this node's neighbors. And then, okay, so there's one more unvisited neighbor, and then we go from here. And then at this point in the algorithm, we would actually like backtrack over like here and see if there are any more unvisited neighbors. But in this case, like if we had like a node like here, then at this point that node would be visited. But in here, it's just like one sort of structure where everything is connected. So that would be our end result. So a DFS tree that starts from here, and we sort of just alternately color these edges. Okay, so let's start implementing this, and let's just see like the input-output format real quick. So firstly, we get the number of nodes and the number of edges. So that's the first two numbers. And then we have, we are given all of the edges. And these edges are ordered. So what I mean is like in the order that they're given. So this is referred to as the ith edge. And this is, for example, like this is the first edge, this is the second edge. Normally this doesn't matter, but in this case it does matter because that's like what we have to output. And if you notice here, so this looks like a weighted graph, so like the numbers on each edge, but this is just like, this is this exact input, except like say for the edge between 1 and 2, I just label that as the first edge, and the one between 2 and 4, I just label as the second edge. So this will be like, this is like a nice visual to have, basically, but it's not actually weighted. If the graph was weighted, it would be like probably a much harder problem. But anyways, let's start coding. So let's take like the NNM from input. And then so here what we want to do is we want to create an adjacency list to store our graph. So let's just name it ADJ, and then we just store it as a list of the neighbors of each graph. So that is, or the neighbors of each node. So that's initialized to like a list of empty lists. And there's one for each node there is. And I believe, so these are numbered starting from 1. So we're going to do like, we're going to just like add like a few cells at the end of this so that we don't go out of bounds. And then we want to, okay, let's just create a variable that stores our answer. So like so we actually want to make it into a list probably, so that you know, because we can't modify a character as a string. So let's just create, and then there's one like character of output per edge there is. So there's like 7 characters of output, 7 edges. First character corresponds to the first edge being colored, etc. So that's that. And then let's take in like all the, oops. So let's take in all of the edges. So U and V, we take that from input. And we basically just want to add it to the adjacency list. So and also something I want to mention is that in Python, if you want to store an adjacency list like this, you can also use something called a default dict. So it's like collections.default or something like that. But that's like a bit slower than the built-in lists, or it uses a bit more memory. So we'll just use this for now. And then let's implement the depth first search. So the depth first search in this problem is pretty simple. So we are just going to implement this recursively. And so the arguments of the DFS method, we are going to just store like the current node. So let's just say node. Okay. And then, so we want to like iterate through each neighbor of this node and then initialize like a new, like call this function itself again from like each neighbor. So we do for neighbor, and then, okay, so we should probably also like store the index of the edges. So we'll just store like this basically. That way we can actually like know like what the index of each edge basically while we're doing the DFS. So we actually care about the index. So node. So this is like all the neighbors of the node, and then like the first one in the tuple will be the neighbor ID sort of, and then this one is like the position of the edge. Since like here we're iterating for I and M, so this would store like the index of the edge. And then for each one, so we would do something like, or actually I think we should probably write it inside this loop. So we check first of all if the neighbor has already been visited, and to do that we sort of need to create a list to store which nodes have been visited. So let's just do that. So visited equals false, and then we'll just do like false for I in range like m plus 1 or something. And yeah, this is just for like the same reason that it's m plus 1 here. And then so we check whether or not it's been visited. So if visited neighbor, then we skip this one. And then we also want to actually mark this as visited. And basically we want to check if this edge has been already processed. So I think this might happen. I'm not sure if it will, but we are just going to sort of cache this in case this happens. But basically we just do if answer and then the current index is a gray edge. So if this has not been already colored, then we basically color it. And here we want to color it like red or red or blue depending on like how far we are from the root. So remember what we had before. I don't think I can bring it back. So let's just say that this is like our sort of DFS tree. And then so this is like sort of depth 1 from the node. So we colored this red. And then depth 2, blue, depth 3, red, depth 4, blue. So in short, it just depends on the parity of the current depth. So if it's like an odd number of edges away from the root, then we color it red. If it's an even number, we color it blue. So this is just so that it alternates. So that it alternates, yeah. And then we basically want to store like the current depth, I guess. So, oh, what happened? Okay, and we don't need to exactly store the depth, but we just need to store like a variable that sort of toggles between like true and false, or red and blue, or something like that. So let's just call this like state. And then this state we'll just make it like either 0 or 1. And then if it's like if it's 0, we'll color it red, and if it's 1, we'll color it blue, or something like that. So if state equals 0, then answer I will be colored red, and then otherwise we'll color it blue. And then at the end here, we will just, or actually when we make like the recursive call, then we will like toggle this. And the way we do this is we do this like little bitwise trick. So we XOR this by 1. And what this does is basically if like the first number, I'll just show you right now. So if like the first number is 1 and we XOR it by 1, it'll just return 0. And then if we do like 0, it'll just return 1. So it just basically toggles it between 1 and 0. So a very small trick. And okay, so I think that is good for our DFS function. And now we just want to basically start from an arbitrary location. And then we want to create the DFS tree. And one extra consideration to make is that this city, so it actually says somewhere here, basically. So it's possible for the entire graph to be disconnected. So that basically means there are like multiple components to this graph. So there could be like a completely different part of the city that's just like, I don't know, isolated from this part. And that is fine. We don't need to like do any extra processing or anything, but we will just like try to run the DFS from every node. Except, you know, after you run DFS, like say from here, then all the nodes inside this group will be marked as visited. So if we like iterate through every node, it won't actually like run the DFS again for each node. It'll just like say, if we arrive here, say, hey, there's a part that's not visited, and then it'll just basically run the DFS algorithm on each connected component. In other words, we're basically creating like a spanning forest instead of a spanning tree. So like a spanning tree for each connected component, basically. And then, so we want to run it from each node. So from 1 to like how many nodes there are. I think that's how it's numbered. And then if it's not been visited before, then we just call the DFS, and then we start from 0. So we start like marking it red first. And then we also just, since I don't think, so like here we're not marking like the first node visited, so we just want to quickly do that. And then finally, we print out our answer. Answer. So we basically print this out. Okay, so I think this should work. Something to note is that there are like a lot of different valid solutions, even like just for this small input. So like depending on how you implement it, like your final answer will be different, but they'll still be correct, hopefully. So let's just run it on like this sample. So no, not from that. So we just do it from here. And then it looks like something is up with our DFS because this is not correct. So let me just quickly see. So let's try this again. So this produces, so let's just quickly check this output. So here we're coloring the first edge red. And then the second one we're doing blue. So this is not like in order or anything, but it's just depending on like which position it's in. And then gray for this one, so we'll just like color it like black or something. And then for number 4 we do red, and then red for number 5. And yeah, so I think that's our final like coloring, and these two nodes are gray. And so if you take a look at this arrangement, you might see like, hey, like the road from here to like here, basically, like from node 3 to node 5, this path isn't like alternating. But remember like the wording of the problem, it basically says like in the end, if there's like a gray road that connects these two locations, then there also has to be like a road connecting these two that alternates from red to blue. And currently, like in this end result, there is no like gray path from node 3 to node 5. But like say if we take like node 1 to node 3, for example, there's a gray road connecting these two. So if they're connected by gray roads, the requirement is that there also has to be a road that is like alternating colors. So here we see like, so from 1 to 2, and then from 2 to 4, and then from 4 to 3. This road will be alternating. So this would, in theory, satisfy the requirement. So let's just test out our program. I suspect there might be like more bugs, but we'll see. Okay, so we have recursion error, and let's just see. Okay, so there can be up to like 200,000 edges. So let's just increase the recursion limit to like 300K or something. So I think like this shouldn't, oops. This shouldn't change like the behavior of our program, but I think this will like solve the recursion error. Because at most, like if it's like a line graph or something, then it'll like recurse like all the way from one end to the other, which will like far exceed the recursion limit. So I think the default recursion limit in Python is like 1000 or something, so it wouldn't work for this problem. Okay, so it's judging, and the checker for this problem might be a bit slow. But anyways, it looks like our code does work. So like proving that this solution works will require like probably more thinking, but in the contest, like a lot of people solved it by just guessing. So intuitively, like this makes sense, but proving that it works every time is more challenging. But anyways, this is my solution to this year's S4. I hope this was clear enough. Goodbye.